Hello, I am going to talk about different scales in sea ice and give some ideas about things we might want to think about when we're modeling at these different scales. And I just want to point out that some of the work I will present is based on field observations from the Mosaic and the Sidex field campaigns and previous field campaigns that are too numerous to mention in here, but there are a lot of people behind this work and they should be acknowledged. And I will like to introduce my group at Oregon State University. Ali, Scott, Mackenzie, Angela, Daniel, and Ben have all contributed, and hopefully you can see the talks of Ali and Scott on their modeling work. Thank you. So, how do we think about a material? If you break a bone, how it breaks is going to depend on the structure at an underlying scale to the macro scale of the bone. And so you can think about a structure as being made up of scales in a hierarchical way, where you have a structure at one scale that makes up the structure at the next scale, and so on. We don't really have a picture of sea ice that looks as nice and clean as this, and that's something that I would like to fix. So I'm going to be talking about what are these scales for sea ice. This is a review of much previous work and the forcing and boundary conditions that need to be considered at different scales. And we need to think about the structure of the underlying scale for any scale that we're modeling, because that structure is actually what's controlling the stress field that we want to model. So the nature of these cracks and discontinuities and the structure at the smaller scale is very important to consider. And obviously we know some things about this, and I will go through that. You have the crystal structure, grains, microstructure, cracks in level ice, ice floes, and then we start getting into realms of not really being sure what scales should be defined. So obviously, crystal structure, there's been much work done on this. I'm going to skip over this because I'm not trying to model at this scale. But within the crystals, you can have defects and cracks that form that are part of the microstructure of the sea ice. And microstructure is made up of grains of ice that have aligned crystals. The ice is growing vertically down, and as it grows, it's rejecting brine, and the c-axis of the crystals can grow into these plates that can have pockets between them. So you'll see that the structure is more aligned at the bottom than at the top, when it can look more granular, as we're seeing in the thin sections down here. So the structure changes vertically to pay attention to. And that structure affects its elasto-viscous behavior and its subyielding behavior. So if you take a chainsaw and cut a section of ice like this, you might see those brine channels through the ice. It's a network of brine channels. And the scale between these brine channels is typically 10 centimeters. And this is very important for controlling the strength of the ice and the speed at which cracks propagate through the ice at the sub-meter scale. Now, obviously, at this scale, we have quite a lot of laboratory and in situ strength testing work that's been done. And I'm not going to say that we have a complete understanding of the strength and material properties of sea ice at this scale, but we at least have a chance to try and model this scale and constrain those models and build empirical rheological models based on actual observations. And I'd encourage you to see Ali's talk about this. When we go to the subflow scale, the scale of sheets of ice, the ice can crack under thermal forcing. It bows, and the tension due to the flexure of the ice is what causes these thermal cracks. So we have a different network of cracks that can be controlling the deformation of the ice at this scale. And note, I'm talking about first-year ice. I'm not going to talk about multi-year ice because it's just simpler for a short talk. Multi-year ice has changes in the structure related to the melt over the summer season. So there have been some experiments done to try and measure the strength of sea ice on these large scales, and I would highly encourage you to look at the work by Cole and Dempsey on this, where pieces of ice in situ were isolated with a very large chainsaw and a flat jack used to do uniaxial strength tests. And the result of this is that the size effect applies from the meter scale up to about 100 meters, meaning that you can apply the same model across these scales, the same rheological model. And I have questions about this work because we don't really know very much about the crack network within the samples before they were broken and how that damage propagated and the behavioral change as the damage changes. So are these intact pieces of ice that were uncracked before the experiments, and what's the effect of having thermal cracks through the ice is not really being explored. On a similar scale, ice sheets actually can move together. So you can imagine pieces of ice moving together that have been previously broken and cracked, and they form these rubble piles or ridges. And on scales of meters in width and hundreds of meters to kilometers in length. So these behave quite differently to other discontinuities in the ice pack. They're essentially, ridges are essentially lines of weakness, and they will consolidate in time. But before they consolidate, we can look at their behavior as frictional, as blocks moving across each other. And there's some work by collaborators with Danny Feltham. I think Danny will probably be at this meeting, so he can talk in much more detail about this, looking at these processes. And they have done a pretty good job at characterizing the frictional processes of blocks that are sub-meter scale moving against each other, which is very useful for calibrating our models. Now we get into realms where we really have very little chance of building an empirical model based on observational data in a standard way. So let's look at the ice pack itself. Andy Mahoney took this photograph of the SizeX ice camp this spring, just to give you an idea of just how messy the ice can look out there in winter. We have multi-year ice and first-year ice all mashed up together and lots of ridges to contend with. One thing that's interesting when you look at the ice deformation in March, the ice is broken up. And back in the 1970s and 1980s, when the first sea ice models were being developed, it was commonly stated that there were cracks everywhere and they were in all different orientations. And therefore, it would be fine to treat the pack as an isotropic continuum. And you could indeed imagine this. And what we do see at the smaller scales is clearly cracks that are related to previous cracks that are moving. So for example, we have here a shear band where there were two cracks highlighted with these orange lines that had existed previously. And as these sheared, they opened up new cracks in between them. So mechanically, we can understand this quite clearly. And if you wanted to model this, your boundaries would actually be those previous cracks that opened, and the scale would be the distance between them. So potentially, we have to think about this scale as an emergent property of the ice pack deformation. And I would just like to point you to Bjorn Ellingson's work, which describes very simplistically with a more Coulomb relationship, how you can relate those boundary conditions through a friction angle to the orientation of discontinuities in the velocity and stress field. So we can think about this analytically if we want to set up our equations in such a way. Those shear zones can propagate in time. And this is just an example from the Mosaic field campaign where we were actually sitting in a shield zone for most of March, April, and May. And between these two time periods, that shear zone expanded, and most of that happened during one particular storm, but it was expanding slowly over that time as well. So you can see this is really just an example of damage in the ice pack. On the much larger scale, we're now looking at the entire Arctic basin. And when we look at visual imagery of the entire Arctic basin, it's quite easy to actually pick out fracture patterns, cracks, that you can almost imagine that you can just see from the pattern of them what the loading was on that that created that fracture. For example, this is an example of arches that formed. During the Sidex campaign, we saw quite a few different patterns of failure in the Beaufort Sea, but mostly were associated with the Beaufort Gyre moving. And we had a reversal event where there was a lot of damage in between those shear zones that set up, or those like between the shearing leads that you can see on the previous image. Let's go back and forward. You can see that happening. And the Beaufort Gyre started rotating around this crack here, this arching crack, and so on. Kind of a beautiful example of the ice breaking up into progressively smaller and smaller floes as you go into April. So the way we can observe this is we can actually get very good observations of the strain field from satellite data and from drifting buoys, and from higher and at smaller scales and higher resolution, we can use geodetic quality GPS, we can use theodolites, we can measure the strain very well. But measuring stress is a different matter, and we can attempt to measure that at points within a region, and we can also localize where cracks were happening acoustically, and we can understand the nature of the cracks acoustically as well. So seismoacoustic work is great on sea ice. So essentially we can measure the strain on the bound, but not stress. And this is very different from the previous examples I've shown you, where you are forcing the boundaries with a known stress and observing the strain. So the only way to solve this is essentially with inverse methods. So there are two camps, I would say, of thoughts about the sea ice scaling behavior, or how it changes across different scales. And I'm not convinced that these two camps are actually remarkably different from each other. The first is this conversation about the sea ice deformation being scale invariant. Essentially, the crack patterns of the whole Beaufort Sea, as we've seen in the Sidex experiment as well, look similar to a lab sample that's breaking in wind crack patterns. I mean, this is just one example of wind cracks from Alan Schulzen's lab. But the argument is that the same kind of model could explain this behavior at different scales. And mechanically, yes, there is similar behavior, but I would say that the exact same model would not fit, because across these two scales, there is a lot going on, and you would not expect the size effect to apply. So you could actually see that there's a nonlinear relationship in the strength between these scales. And the reason I would say that is if we start looking at the total deformation on different scales, so I can take a buoy array like the one that was put around the Mosaic field campaign and split it up into smaller and smaller scales and calculate the deformation for each of those buoy triads that's plotted here. And then I plot up the buoy triads, and I plot the times, essentially every data point of deformation against the length scale, which is the square root of the area of that array. And for each range of sizes or range of length scales, I find a mean, and then you plot a linear fit to those means. And there is not a linear fit. There is essentially a break somewhere around a length scale of 10 to 30, 40 kilometers, where it doesn't really make sense to be fitting a linear trend to this. And it could be that there's a gradual change over time. It could be that there's two different relationships at the smaller scales. There's a lot going on here that we actually need to understand. But the main point is the size effect does not apply at this scale. Other people have talked about hierarchical scales. So like the bone fracture, the material itself has structure that you would expect there to be a hierarchical change in behavior as that structure changes. And for sub-flow scale, we understand this fairly well. As we're going into the regional scales, we might be going through different aggregate behaviors. And McNutt and Overland, then McNutt, determined that these scales that she defines here from kinematics of the ice pack. And there is some question about whether this aggregate scale exists and what the multi-flow scale really means. And I can tell you for sure the coherent scale exists because I have observed it. And if we were to look at a spectra of the total deformation, so this is kind of essentially thinking about the timescale properties, because you can relate the spectra to a fractal dimension, we can see that at the largest spatial scales, the ice deformation is behaving as red noise, and it becomes increasingly whiter as you go to smaller scales. So there's more noise at smaller scales. And if you think about this process being at the largest scales driven by the synoptic wind forcing, which is red noise, and the interactions with the coastline, the boundary condition, this makes sense. As you go down to the smaller scales, you have intermittent behavior in the ice deformation that is showing up. And you have different boundary conditions because the ice is being broken due to failure between shear faults that are already existing. So intuitively, this makes sense, but you'll notice that there's really no separation in those scales. It's very hard to separate them. So I'm not sure that there is a clear hierarchical model popping out from this analysis. And if we were to look at a buoy array, say a small array in the middle of a large array, and we look at the coherence between the divergence of the large and small array, this is a cross-wavelet coherence. So we have period up here. This is the semi-diurnal period, which is the inertial oscillation. Notice that we see that. This is the synoptic period. So we see that there's enhanced coherence between those, the deformation, the kinematics of those two buoy arrays at 4 days and at 8 days. So on longer ranges than the synoptic, the ice is becoming more coherent. We are feeling the boundary condition and the weather more. So this really just points towards that concept of Lynn McNutt and Jim Overland as being correct, that there is an emergent scale that comes out. So to summarize all of this, we can take a multi-scale view of the sea ice, but first we need to define the scales and how those material properties change across these scales seasonally and regionally. This is something that my fieldwork is going to be hopefully giving some insight into, and working with a lot of people to do that. So in this multi-scale view, we might view that within a scale invariance could apply. But really it's the boundary conditions that are defining the scale. And across different scales, we might not expect that. And so both these viewpoints are valid, and we just need to put this information together to sort out what the scales are. And the important point here is taking this philosophy as you can define your models and design your models for particular scales that are emergent in the properties of sea ice. Oops, other direction. And I have attempted to pull together a figure that shows these different scales. You'll see the photographs from the presentation. And I point out that there is this in-between scale between the flow scale and the pack ice scale, where we really need to develop a better understanding of what is the boundary conditions and forcing that's controlling the cracking that is underlying the largest scale that we model. So this is the important question to get at as to whether the sea ice is isotropic or anisotropic. And I hope we can do some work to sort that out. I'm hoping to write some papers about that. So that will be my ongoing research that I'm happy to talk about in person. So I will point you to some talks if you're interested in learning more about this. My AGU and EGU talks are talking about the mosaic, identifying scales over which sea ice kinematics are scale invariant, and seasonal transitions, that's ongoing work. I would very much like to talk about the SciSex campaign and what we can do to support DEM modeling in the future. I would really encourage you to look at Ali's talk and Scott Dursky's talk about modeling at 2 different scales that my group is doing, and in particular Scott's work in developing a model that can be used at a regional scale, because regional scales are not well constrained. And this is the direction we're going, is hopefully we can use the SciDex data to constrain these models. And we also need to understand and develop new ways to do this with inverse methods. And I'm looking forward to improving future models. So thank you very much for your attention. And if you have any questions, I'd be happy to answer them over email, in the chat, however you like. Thank you. Bye.